My name's Alan Beresford. I'm Managing Director of Eco Cooling Limited, and in the next half hour or so I'm going to give you a presentation about evaporative cooling of data centres and server rooms. And to explain it best, I thought it would be appropriate to do a case study to see what it's really like there out in the field. The company I'm going to talk about is a company called M247 up in Manchester. The reason I'm going to talk about M247 is it's a very professional, well-organised, traditional data centre with conventional equipment. And they were looking for a retrofit solution with nothing too complicated or too bespoke. They've got their 500 kilowatts of load, a conventional raised access platform floor, conventional cracks, conventional racks. And they're running at a very good level of efficiency for that type of data centre. What we call a PUE, a power utilisation effectiveness. Now, what do we mean by PUE? Very, very important concept. We look at an efficiency of a data centre and its energy use, or a server room, by looking at the total rate, the ratio between the total energy used against what's really useful work done in the IT equipment. Now, many data centres in Britain run at a PUE of anything up to 2.5. Now, the only way you can get to using more energy in your ancillary equipment than in your IT equipment is really by putting it into the cooling equipment. Many people are absorbing as much energy in their cooling as they are in their IT. Now, this is obviously an incredible cost, both in terms of the electricity usage and its carbon footprint, and also the consumption of the available power, where many sites have run out of available power. So, we look at this ratio called a PUE. You'll also come across another expression called a DCIE, a data centre infrastructure efficiency, which is purely the inverse of it. It's like a percentage efficiency. So if you look at your 100 kilowatt data centre, typical thing, you'll have 100 kilowatt going into your IT load, maybe 100 kilowatts going into your cooling system, and 8 kilowatts into things like UPS losses and distribution losses and transformers. Good data centre, like M247. Running at about 1.6, but still probably 50% equivalent of their IT load going into their cooling system, using good quality cracks. Now, what I mean by a crack is a computer room air conditioner, your Airedale, Denko, that type of piece of equipment. Using good quality equipment with all of the extras to maximise the efficiency. However, that's still quite a cost load and quite a significant carbon impact. So what can we do to improve things? If we use a ventilation system and use evaporative cooling instead of refrigeration, then it is technically possible to achieve a PUE of 1.1. That's an incredible level of saving, and in some cases, you know, it looks too good to be true. But what I'll try and explain over the next few minutes is how we really achieve that using simple engineering and in a simple modular system designed specifically for the IT sector. At the end of the presentation there'll be an opportunity for questions, so please, if you could wait till then, it would make things a little bit easier for us in terms of presentation and timing. How does it work? Well, it's no more complicated than air and water and their relationship. In the UK, when it is hot, the air is also low in relative humidity. And air is like a sponge. It loves to soak up water. If we put this air in contact with a wetted filter pad, water will evaporate into the air stream. The heat required to change the water from a liquid to a gas comes from the air, which then cools down. And we incorporate these wetted filter pads into a thing called an evaporative cooler, which is four wetted filter pads with a water circulation system and a fan to move the air around. And we build this into a device called a CREC, a computer room evaporative cooler. Straight away, let's get to the numbers. Let's look at what we were trying to achieve at the planning stage with M247. As I said earlier, M247 is a 500 kilowatt, half megawatt data center. So on the lower third in terms of the size of data centers you would come across. When we look at a data center, a lot of people do get a little bit misled in that they do concentrate a little bit too much on the actual cooling load. There's a little bit more to it to that. What we're actually trying to do is give all the servers the right volume of air. Wherever that air comes from is irrelevant, but you've got to give it the right volume. Now, 500 kilowatts of servers actually adds up to about 42 cubic meters per second of air. That's a lot of air. Where does it come from? The next stage of that spreadsheet, you will see there's a comparative cost, 2 columns, between refrigeration and an eco-cooling CREC system. The coefficient of performance of refrigeration in a PUE 1.6 data center will be about 2. That means for the 500 kilowatts of IT load, we will be putting 250 kilowatts of energy continuously into the cooling system. The equivalent capacity of cooling delivered by an eco-cooling CREC system would only require 21 kilowatts of electricity. So you'd see 92% less energy put into that system. A very considerable difference. Now down to the finances of this. 8,760 hours in a year. We can't get away from 24/7, 52 weeks. A lot of hours. So the M247 project, if they'd have gone down the existing conventional CREC route, would have been using over 2 million kilowatt hours of electricity per year. The eco-cooling system would require less than 200,000. And at 6.5 pence a kilowatt hour, their annual running costs for the CREC system would be 140,000 compared to just over 10,000 for an eco-cooling system, with a potential environmental benefit of saving over 1,000 tons of carbon as well. Big numbers. However, there are a few things that we mustn't lose sight of when we start doing a project like this. We mustn't lose sight of the real objectives. The primary objective is, can we keep a stable and secure environment for these servers? Many businesses, the server rooms and data centers are central to their business process and cannot afford any risks whatsoever. We have to give these pieces of equipment the right quality of air and the right level of security. And then the big wish list. We want low cost, low cost, low cost of everything. We want a low environmental impact where possible. Let's use less electricity, let's have less of a carbon impact, and also if we can avoid the use of refrigeration, then we can avoid the use of refrigerants, which have their own separate environmental impact. Security and resilience, or redundancy. We have to build in security, we have to build in fail-safe systems so that when things go wrong, as we can never legislate against, we've got appropriate backups. And where possible, where can we make this simple? What most people are looking for is to concentrate on their core activities, not having to become experts or having high technical skills to look after their infrastructure. So let's look at the operating conditions that are required in a data center. And here we've got a typical, this is the Ice Colour, which is a separate company which is owned by M247. You guys are familiar with data centers and server rooms will recognise the cold aisle containment. In that cold aisle containment, we're pushing air up through the raised floor, through grills, and we're trying to achieve the following: the right temperature, humidity, cleanliness, and redundancy. However, many people in the sector don't currently understand what the modern standards are for those parameters, and that's what I'll explain over the next couple of minutes. So let's look at temperature and humidity. Left side of the axis is relative humidity, temperature across the bottom. Now, most people believe they've got to maintain their data center or server room in that patch there, around 21 degrees centigrade and around 50–55% relative humidity. That's what people have been brought up knowing and believing. Why? Well, we know if we increase the temperature, we'll start to get equipment failure. Things will blow up at high temperature. What a lot of people don't appreciate is if you increase the temperature of air going onto a server, the little fan starts to speed up and can consume an enormous amount of energy itself. Low temperatures. Now, most low temperatures and the standards which are set are an economic, not a technical standards. These standards are set to stop people running their refrigeration equipment too cold and losing further performance. High humidities, high relative humidities. Everyone knows if we get condensation in any sort of building or any sort of equipment, that's going to lead to problems. With printed circuit boards, there is also an issue of a thing called CAF development, which is a filament development which can grow on printed circuit boards and can cause failures. But that only happens at high temperatures and very high humidities. Low humidities associated with tape stability, the old paper tapes and paper card systems. And also low humidities have been associated with a thing called ESD, electrostatic discharge. So people in the data center and server and IT world appreciate these factors exist, but many people don't understand where the modern lines are drawn. So let's look at a few standards. You would expect IBM to have some fairly rigorous standards. You take a standard server from them and suddenly you see that temperature spec is 10 to 30 degrees centigrade with relative humidities 8 to 80%. When people look at their equipment, most of them have never been given the environmental operating specifications, and that's a surprise to most people. That's the key reason why we can start using a radically different form of cooling for modern equipment. So if we go back to M247, you will see in Manchester, it's cold most of the time. Okay. On that graph there, you can see the red line is the ambient temperature, and the blue line is the temperature of the air coming off what's called a 90% efficient evaporative cooler. The ambient temperature will just reach 25 degrees centigrade, but with a bit of local heating, southern facing buildings, you might really get a true inlet air temperature ventilation system of about 30 degrees centigrade. However, passing the air over one of those wetted filter pads means that the air temperature would never normally go above 20 degrees centigrade. So that simple wetted filter pad in an evaporative cooler will give us an unlimited amount of air below 20 degrees centigrade without any need whatsoever for refrigeration. Let's look at this on the psychrometric chart. Psychrometric chart is the tool that engineers use to understand the relationship between air and water. There is temperature across the bottom, the horizontal axis, and specific humidity vertically. The hotter air gets, the more water it can support. Most data centers and server rooms have been designed to those guidelines. The typical UK guidelines that you find from CIBSE, Chartered Institute of Building Service Engineers. 19 to 23 degrees centigrade, 45 to 55% relative humidity. That is what your close control crack is designed to do. However, if you go to the 2008 ASHRAE standards, which is the American Society of Heating and Refrigeration Air Conditioning Engineers, they revised their specification in 2008. And this is the standard that you would use if you were going to build, let's say, a tier 4 data center of the highest standard of resilience and redundancy and reliability. Their new standards are 18 to 27 and talk about dew points rather than maximum humidities, dew point of 15 degrees centigrade in that yellow patch. But they also give us a little bit of latitude as well, and that's the design conditions. But ASHRAE also provide an allowable zone which you're allowed to drift into short space of time. Now you see, this zone that we need to operate within, even to operate the very highest level of reliability data centers, is really starting to grow. If you look at your equipment, that's a typical specification for modern equipment. Really quite a wide range. If you take a ventilation system with evaporative cooling, you can put yourself into a zone there and provide 100% temperature compliance and about 99% compliance against ASHRAE Class 1. Now I'll explain how from that we can engineer and implement a system to actually exploit that. What was the solution then for M247? We use these modular boxes to fit around buildings as part of a balanced ventilation system. Air is pushed in, it sometimes goes over the pads which are dry or sometimes wet, cooling or just fresh air into the building and recirculating around. Now many people have existing data centers with legacy equipment and require retrofit. So we have to have a number of installation methods to implement this. And this is what we actually ended up with. These are two stacked coolers sitting at the bottom there, with side discharge coolers pushing air in through, remove a window and allow the duct to go in there, which then goes into the raised floor. The top duct is air which is returning the hot air from the hot side of the data center. One of the key issues with a ventilation system or a true free air system in Northern Europe is the air is actually too cold most of the time. So we have to heat it up. And we do that by creating a temperation loop which brings that hot air back into the cooler to warm the incoming air up. So we came out with a solution. They're 500 kilowatts, required 14 of those eco-cooling CREG stacked in that way. Now that gave us N+1 redundancy on the CREG system, but we didn't move completely away from refrigeration. We put in an equivalent capacity of refrigeration, brought simple cracks to the full volume. And we did that for really one prime reason. If you've got a ventilation system, you have to have a plan if there is a fire, either internally or externally. Most data centers will have a fire suppression system in place. You have to be able to seal the room to contain that fire suppressant. You can't do that while you've got a ventilation system running, providing the cooling. That is when you have a system which then switches the refrigeration-based cooling back on in an internal fire condition. Secondly, you've got another issue if there's an external fire. You don't want to be bringing these carbon deposits from an external fire into the building and into your IT suite. Therefore, that's another key requirement of why you need an additional system to provide the cooling when you've got to shut the ventilation system down for an external fire. What that happens then is we actually end up with a two-end solution. We have a complete refrigeration system and a complete evaporative cooling solution. A lot of you will now be thinking, well, this is going to be an expensive solution. Not necessarily, because the evaporative cooling system is a relatively low-cost capital investment. And if you look at the savings which are achieved, most cooling systems are paying for themselves, have a return on investment of less than 1 year. So to balance the two is a very sound economic move, both capital and operationally, and you can end up with a very high degree of resilience and redundancy. This is a cross-section, a simplistic view of how it all works. We have an evaporative cooler, which is providing air through an axial fan, down discharge, and into a raised floor. We then go through the tile, the grill that you see on every conventional raised access floor, going into the cold side of the racks, where the air is pulled in by the fans. It then comes out through the hot side, and then is exhausted out of the building. There we have a damper which allows that hot air to come back into the centre of the cooler and mix with the ambient air which is going over those filter pads. For 90% of the time we will be running on a fresh air system, just using the hot air to warm the ambient air up to give us compliant conditions going forward, typically about 20 degrees centigrade. Just as a slight aside, when we commissioned M247, we started with a set point of 20 degrees centigrade. As time's progressed, we've actually reduced that, and it's now running at 17 degrees centigrade. The net result of that is, whilst we're achieving the cooling savings, we actually reduce the net IT load as well by running the servers at a lower temperature. So the PUE looked good, but also the net use of the IT went down as well. Now this system, which is a patented system by Eco Cooling, provides us with this constant flow situation, which is sized to match the requirement of all those little servers, and giving us a constant temperature. We put no humidity control whatsoever into the system. The telecoms industry haven't used humidification for years now, so we're not really changing anything there. The thing that might be relevant to some people is funding. The M247 project was funded by a loan from the Carbon Trust because they're an SME. The rules have changed slightly, and last year the M247 organisation got a £350,000 interest-free loan to do the whole development. Another company in Bedford received a £500,000 loan. But unfortunately the Carbon Trust have rewritten the rules now, so the maximum is £100,000 that of an interest-free loan that an SME can get. There's also another organisation called Salix, which is an equivalent scheme but for the public sector, and these systems also qualify within the Salix funding scheme. Control. Control is at the heart of all systems in the IT. Many ventilation systems are put in a very simple way and don't offer precise control or communication. In this system here at M247, we put these coolers in pairs, the stacked pairs of coolers, and each cooler has its own PLC controller, which is then linked to a master controller. How we control a computer room set is on two things: temperature and pressure. We monitor the pressure, in this case, of the raised floor, the underside of the raised floor, because we know if we're achieving, in this case, 20 pascal of pressure in that underfloor, we're getting the right flow. And a key part of commissioning is to understand how your raised floors are working and how your total flow rate of the server room is operating, what is required, and give it the right amount. Also, it gives us a control measure. If something fails that we haven't been able to pick up automatically or electronically, the pressure will drop, the system will see the pressure drop, and all the other cooling systems and their fans will ramp up their speed accordingly and raise an alarm condition. All this is linked together through what we call our correct control panel. Within a correct control panel, these PLCs, we are using a microprocessor controller using the called Boolean logic and or NOT gates, but that gives us full what's called analog control. We can measure true temperatures and true pressures and true conditions, and that's all linked together with also this facility for either Ethernet link into your existing network systems, or if using building management systems, and Modbus to communicate in one direction all the operating parameters of temperature, pressures, fault conditions, etc. And then as an input, temperature set points, alarm conditions, fire alarms, smoke alarms, fire suppression, purge requirements, etc. All linked together on one common control system. What did we really end up with? Now, I said that M247 are a well-managed business. Many data centers don't really measure themselves at all. Some data centers measure themselves in a very crude way. M247 look at themselves every 30 seconds and know what's going on. They're monitoring their PUE temperatures continuously, and they're calculating their PUE continuously. And you can see there, after this was installed, we were getting a PUE of 1.2, 1.18. I think the lowest I've seen there is 1.17. Now, for these guys to achieve less than 1.2 is a real world-class performance. Google claimed to have the most efficient data centers in the world of about 1.2, 1.22. You see some very bespoke designs now being put forward, but are really based on very, very custom engineered solutions for fixed size data centers. To take a legacy data center and retrofit a simple piece of equipment and achieve this world-class performance is a position which they're rightly very proud of. And, of course, financially makes a very big difference. Privately owned business, so the guys making the decision are clearly in tune with their decision making. David Buckle, the very capable guy, the MD, very conscious of the performance. This project delivered exactly what he wanted. And in terms of Chris Bird, the technical director, equally important is the consistency and the reliability of the equipment and the consistency of the delivery of the conditions within the data center. And last year, you see, we did have a warm period for a few weeks last year. First warm year we've had for probably 5 years. That system where I explained we could turn the cracks on, you can also use that to turn the cracks on if you have an over temperature situation. Last year there was no requirement to switch the cracks on at all in this installation. So what can we do? Using fresh air systems and evaporative cooling, we can create compliant conditions for modern IT equipment. Modern IT equipment is robust. It has a wide operating temperature range. It has a wide operating humidity range. It doesn't require perfectly sterile, perfectly dust-free conditions. We don't have open drives, we don't have open bearings now. Your modern kit is robust. If you embrace that widening of those operating standards, then you can implement a ventilation scheme based on these principles and reduce your energy bill of your cooling by over 90%. Now, in most cases, that means that you can reduce the energy usage of your data center by a half, with a capital investment which could pay for itself in under a year.